Okay, so let's get started. Abel, you have to close the computer. All right. So what I wanted to do today is to start a new topic, which is consistency and replication. But before we do that, just a few announcements. I think lab 2 is done. Okay, I will hand out lab 3 soon in a few days. It will be due on 1st of May. Okay, remember that labs are due the 1st of the month. We'll do that. But before the lab is due, I'll also hand out a homework. We haven't had a homework in some time because we had spring break, then we had exams. So I'll do that. There are a couple of lablets remaining. We'll start handing them out soon. Okay? And after lab 3, we will be done except for the final exam. Right? So today we'll talk about consistency and replication. We'll start with, yes. Okay, question is how many lablets and homeworks do we have pending? There are 2 more homeworks. Okay, so 2 before the midterm, 2 after the midterm. And I think there are either 2 or 3 lablets. I have to check. There are at least 2 lablets. Last year we had given an optional lablet as extra credit. We'll see if we give that. Okay. What is lab 3 about? Okay, so lab 3 is going to be related to what we discussed today and subsequently. So it will involve replication. You'll have to replicate your services. So far you went from a simple application to microservice. Now we'll replicate it. We'll put caching, add cache consistency, so improve performance. And then there may be some other aspects to it, which might involve a cloud deployment. Because right now you did a Docker deployment, so there will be a cloud deployment. So I think those are things we'll add to lab 3, right? Okay. So this is why this topic and the next one that's going to come is going to be somewhat important because we will take these ideas and put that into the lab. Okay. So let's start with the replication. Okay. So the replication I'm going to talk here is going to involve more data replication. Remember that you can replicate the compute or you can replicate your data. Okay, this is done for different purposes. Today's lecture is going to focus more on the replication of data, which is really a common technique in many distributed applications. There are 2 reasons why you want to do replication at all. Okay, one is to improve the reliability of your system. If one copy of your data goes down, this is true even for a compute replica. If one of them replicas is down, you can fail over to the other one. So your data or your service continues to be available even if there are crashes or there is some corruption of data. Okay, that's one reason to do replication. The other is performance. Okay, the more replicas you have, the more requests and more users you can service. So you can scale your application's performance with the number of replicas. Okay? There are 2 types of replication you see in this context. One is replicating at a single site. Okay? That allows you to essentially, let's say, replicate web servers and or web services. Okay? That's going to allow you to serve multiple users. The other is you can replicate geographically. You can put one replica, let's say, if you have users across the world. Okay? If the users are far away from the service, they see a higher latency to get to the service. So in this case, if you put replicas in different regions, then the users can go to their closest replica, which gives them better performance. Okay? So large services will actually have geographically distributed replicas where they might put replicas on major continents or in countries where they have users and so on. Okay? So those are the 2 reasons for replication. One is to improve reliability. The other is to improve performance. Okay? And there are a few other issues that are involved when you think about replication. We will largely come back to them when we talk about the World Wide Web. Okay? So we will look at replication in that specific context and see how to address these issues. And these issues really relate to, first of all, when to even use replication and when not to. Okay? If you use replication, what is the degree of replication? How many replicas do you want to create? Okay? And where should you put the replicas? Okay? If you are going to do this geographically, where do you want to put your replicas, what impact does it have on your users, and so on. So those questions which relate directly to issues of replication, we will hold off for today, okay, and come back to them later. But what we'll do today is to talk about an important aspect of replication, which is consistency. Okay? The moment you create copies of your data, okay, if you make a change to any one of the replicas, you have to ensure that the change is seen by the other replicas. Otherwise, the other replicas go out of sync. They have older data, and if that older data is read, bad things may happen. Okay? Your application might give incorrect results to the user, or users might make decisions based on outdated information. So you don't want that to happen. Okay? So to ensure that that does not happen, you have to do extra work by implementing what is called cache consistency, okay? Or not even cache consistency, consistency. Okay? You also have to do this when you replicate in caches, but you have to maintain consistency of your replicated data, which means that you have to keep them in synchrony with one another. Okay? And today we are going to look at techniques to actually do this. Okay? And there are a set of things that we will get to when we think about consistency. Before we do that, I wanted to mention this very famous result that has to do with replication and consistency and things of that sort. It's called the CAP theorem. Okay? Here, CAP is an acronym, stands for consistency, availability, partition, tolerance. Okay? It was a conjecture almost 25 years ago by a very prominent distributed systems researcher from Berkeley, who made this conjecture at a conference. And basically what he said at that point was, if you take any web service or any distributed service for that matter, does not have to be web service, okay, it is not possible to have all three of those properties at the same time. Okay? You cannot ensure consistency, which means that nodes will see the same data at the same time. Availability, which means that even if some nodes fail, users can continue to write to other nodes in the system, which means one failure does not bring down the entire system. That's called availability. And partition tolerance, which means that the network gets partitioned, or the network is not available, makes some of the nodes reachable, even then you can have the system running. Okay? So all of those three properties are desirable. Okay? You want to have replication, and you want to have consistency. Of course, you want to have availability. That's why you had replication to begin with, that if some nodes go down, so you can continue to use the system. And if there is some network issues, you still want some of the nodes to be reachable. But the conjecture was you can at most have two of those three properties at any given time, but never three. Okay, not all three. Okay. We are not going to go into a lot of details as to why. There is actually a proof that the theoreticians wrote soon after this conjecture was made that formally proved that this is going to be the case in any distributed system. We will not actually look at that proof here. Instead, we'll just look at some example just so that you get some sense of what this CAP theorem is about and why we need to keep in mind. Okay, so in some sense, you should not, as a distributed system designer or a software engineer, think that you can have all three properties in a system. Fundamentally, it's not possible. Okay? Something you need to, it's an impossibility result you need to keep in mind. Here are some examples of systems that provide two of the three properties. Okay? So first one is consistency plus availability, which means that you cannot, you do not worry about network losses and so on. So if you have cluster databases and things of that sort, and a two-phase commit, which we haven't actually seen so far, okay, these types of systems, or even a single database, okay, will give you consistency, okay, which means that you can keep the database replicas consistent. It gives you availability, which means if one of the replicas fails, you can continue to run the system. Okay, but it does not give you partition tolerance, because the network is down, you cannot reach the replicas, then of course you can't do anything in this case. Okay? So, and that's true for two-phase commit also, but we have not studied that yet. We'll come back to it in 2 or so classes. Okay? So the second example is so that one gives you the C and the A property, but not the P property. The next one says we can have systems that give consistency. Oh, your question, yes. Okay, question is, when you say consistency and availability, does it mean the node or the database? Is that your question? Okay. Right. Okay. So in this case, I think you should think more cluster databases than single database does not actually have availability guarantees typically. Cluster databases do. So let's ignore the single database for now. Just think about cluster databases. So in this case, it does not matter whether it's the node or the database, they are one and the same thing. But you are right. If it's a single database, that distinction is important because the database goes down, nothing is available at that. Right. So that is absolutely true. Okay. All right. So other examples, consistency and partition tolerance, but no availability. Okay. So essentially things like distributed locking, right? So we talked about locks 2 or 3 classes ago. Okay. So in this case, if you actually have, we had cases where if some nodes went down, you couldn't get a lock because you could not, there was either a deadlock or some other problems cropped up with the coordinator went down. So you could not tolerate losses of nodes, but essentially there was consistency and there was partition tolerance in there. Okay. So, but no availability. If nodes failed, you could not deal with it. Okay. And the last one, which actually we'll see quite often when we get to web and so on, says you can have availability, which means that you have replication and nodes continue to be available. Even if the network goes down, some nodes are available, but no consistency. Okay. So this is in the context of web caching and DNS, where you give very loose guarantees on consistency. Because you can say, if some nodes are not reachable, fundamentally you can't keep all the replicas consistent. Okay? Because if one replica changes, it cannot tell another node that it's another replica, that something has changed. If there's partition tolerance, if the network does not let you even contact the other node. So you will have to give up consistency if there is no, if you want to have partition tolerance. You want to be able to continue to operate without contacting other replicas. Because that's an example where you have the A and P property, but not C. And there are many other examples, some of which we have not actually studied yet. They'll come in later classes. Okay. So in any case, I think this is something you need to know, that when you design systems, at least distributed systems, there are 3 desirable properties you want, but you cannot actually have all 3. So as you have to decide which one you want to give up, okay, which are the 2 more important ones, because you will not be able to do all 3 in any system. Okay, this is a database example which I will actually let you see offline. Okay, this is showing you all kinds of databases that you may have encountered, things like MongoDB, Cassandra, Vertica, MySQL, all kinds of databases, and it's trying to say for all of these database systems, which of the 2 properties did they pick. Okay, so you'll see that things like MySQL essentially don't do partition tolerance, but do consistency availability. The things like MongoDB, Memcached, and so on, they cannot deal with the availability. They choose consistency and partition tolerance. And then there are others like Cassandra that do availability, partition tolerance, give up on consistency. Probably if you're not heard of these products, don't worry about it. It's just an example to show you, just even within the context of just these databases that are used as backends of web applications, they have made these choices so you can decide which one to use for a specific web application. Okay. All right. So with that, let's now get to replication and think about more consistency models. Okay. So here, this picture is actually showing you 2 different approaches for replication. One is called application level. So the application is responsible for replication. The application deals with ensuring consistency. Consistency maintenance is the responsibility of the application. Okay. And the second one, which is the second picture here, is a middleware-based approach where the application doesn't actually deal with consistency. Okay. There's a middleware system that is aware of the replication, that tracks the changes, and is responsible for ensuring that the replicated objects and so on are kept consistent with one another. Okay. Now, in either of these 2 approaches, whether the application doing the work or the system doing the work for the application, you still have to implement a consistency protocol, okay, which is the protocol that's going to ensure that if a change is made at one replica, other replicas are going to see. Okay. So we'll now see how can you actually implement these ideas, or at least not how you implement them. Implementation will come later, but what are the types of guarantees you can give on for consistency? And we'll see that there's a spectrum. It's not just one approach to maintaining consistency. There's a whole slew of approaches, and it's good to understand what they are and what their guarantees mean and what the trade-offs are. Okay, so to do that, let's start thinking a little bit about what replication and scaling mean and why even we worry about different types of consistency guarantees. Why not give the best possible guarantee, which we'll see is called strict consistency. Okay, and the reason is that consistency maintenance comes at a cost. Okay, and you have to pay the overhead of ensuring all your replicas are consistent, and the cost can be quite high in many cases. Okay, so the real issue is what kind of price are you willing to pay to ensure that your replicas are consistent with one another, because this is extra overhead that you have to incur when you have a replicated application. Okay, so let's take an example to understand when you may want to pay that price and when you don't want to pay that price. Okay, so let's just take an object. Doesn't matter what the object is. Let's say it's a file. It has n copies. Okay, it's replicated n times. Okay, let's say that the read rate on this file or the read frequency is r. Okay, some value r. The write frequency is some value w. Write frequency is how often the file is changing. The read frequency is how often is the file being read by you. Okay, so let's take two cases. Okay, the read frequency is much smaller than the write frequency, which is r less than w, and the opposite. The read frequency is much higher than the write frequency. Okay, so let's take the first case. Okay, the read frequency is lower than the write frequency. Okay, what does this mean? This means that the file is changing very frequently. The write frequency is high. Right? But the read frequency is very low in comparison. It's relative. Right? So it's changing frequently, but it's not being read often. Okay? So it's a file that changes a lot, but not many users are reading that file. Okay? So now assume that you want to keep the file consistent. So every time the file is changed, okay, you will have to tell all the n copies of the file, all the n replicas that the file has been modified, maybe propagate the new version of the file and so on. That is what a consistency protocol will do. Okay? And this is going to happen often because the file is being modified quite frequently. After every change, you will have to do all this extra work to let the replicas know the file has changed. Okay? But you do all of this, the file is not being read. Right? So maybe you do 100 writes and you do 1 read. So they will say do this 100 times, but nobody is reading the file. So all of that extra work is not being used by any reader that's actually reading the file. Okay? So you're paying a high cost for maintaining consistency, but you're not getting any benefit because there are not that many reads in the system. Nobody's actually reading whatever has been modified. Okay? That's one approach. Not one approach, one scenario. The other scenario is the opposite. Okay? The file is being read frequently, but not modified frequently. Okay? So maybe it's modified. It's like the web page for the course, right? It gets modified twice a week before the lecture. Okay? Maybe there are lots of reads because you all are maybe coming and looking for the slides or something like that, right? So it's the opposite case. Now, in this case, because the writes are infrequent, but the reads are frequent, you want to make sure that any read that comes always sees the most up-to-date version of the file. Okay? It is beneficial to make sure after every change, all the replicas are updated because there are lots of users accessing the file. Why should they see an older version? Okay? So in this case, you may want to pay the cost of consistency maintenance because it's paying off. As soon as the file changes, there are lots of users trying to see what has changed. So maybe you should keep the copies consistent, and then users are happy. They see the most up-to-date version of the file or a web page or whatever the object may be. Okay? So these two examples tell you that strict consistency, which says keep all the copies always consistent, might sound like a good thing, but because it has a high cost, you got to think about, do you really want to pay that high price? Okay? When does it make sense, okay, to pay that price? So that's the scenario you want to keep in mind. And what we'll see is you don't always need to have strict consistency. We'll give you a spectrum of weaker guarantees. Maybe you don't want to pay the high price, and pick a weaker guarantee and say, I will only guarantee you this as opposed to the strictest possible guarantee. And that may be enough for many applications, specifically applications where the read rate is much smaller than the write rate or something like that. Right? So this is why we are going to study maybe 6 or 7 different approaches to doing consistency, and we'll start with the strictest one and then end with the weakest possible. And you'll see the entire spectrum as we go one at a time. Is this clear? Any questions so far? Okay. So let's start with consistency semantics of the consistency model. Okay. So this is the picture you want to keep in mind. Okay. Though you see that there are 3 disks in the picture, that's our data being replicated. Okay. And you see the boxes at the top, those are users or processing, accessing the data. Okay. So in this case, in this trivial example, there are 3 copies, but typically there will be n. Okay. And then there are users accessing the data. And the user tries to access the data, maybe they go to their nearest copy to access it. Okay. And then the idea should be that that copy should be somehow consistent with other copies. Okay. What does consistency means? It basically means that you always want to return the results of the most recent update, which is the most recent version of that object, which is also another way of saying that is you want to return the results of the most recent write. The most recent write is the one that updated that file. So you want to return that version of that object of the file for a subsequent read. Okay. And you'll see that even the definition of what is the most recent update is not actually going to be clear depending on some consistency models. Okay. So keep this in mind. So we'll start with one at a time. We start with strict consistency. Okay. The idea of strict consistency should hopefully be intuitive. Okay. It says that whenever you try to read a replicated data item, a replicated web page, replicated file, okay, you will always get the most recent version. You will never get outdated. No matter how many copies there are, when you say, I want to read it, whatever comes back is guaranteed to be the most recent version. Okay? That's called strict consistency. Very simple. Okay? So this is going to implicitly assume, okay, a global clock. Okay, because you can say, what does it mean to be the most recent write? First thing is you got to timestamp the writes to know if there are multiple writes in progress, which is the most recent one. And remember, this is a distributed system. So there may be one write on one node, another write more or less at the same time on another node. Unless you have a perfectly synchronized clock, you don't know which is the more recent one. If you don't know which is the most recent one, or the system doesn't know, how is it going to guarantee you that you are getting the most recent? Okay. So this one assumes strict consistency, assumes global perfectly synchronized clocks, so that there is no ambiguity in knowing which is the most recent write. Okay. Your clocks are out of sync and you just timestamp the write. You don't know, okay, when there are 2 writes, if you look at the timestamp, which is the more recent. Okay. So clock synchronization has to be assumed, and the perfect clock synchronization has to be assumed. Okay. That's the first issue. Of course, you know there's no such thing as perfect clock synchronization. We already looked at that when we did clock synchronization. Okay. That's the first thing. The second thing is, as soon as you make a write, okay, it has to be immediately visible at every replica. Okay. Because you can always construct a case where a write happens at time t, and there's a read at some other replica at time t plus epsilon, where epsilon is very, very small. And you have to make sure that write result has to already have reached the other replica. Otherwise, it cannot return the most recent. Okay. And you should also realize that that's fundamentally impossible to achieve because there is always network propagation. Okay. Maybe it takes half a millisecond for the write to propagate. Okay. What if the read comes quarter millisecond after the write? Okay. As per this guarantee, you have to return the result of the read, but that's not even possible because you can't send information faster than speed of. And that's the fastest you can propagate information, but this one assumes that you will almost instantly make all the writes visible. So fundamentally, strict consistency, okay, in the strictest possible or the purest definition is actually not possible, because you can't have perfect clock synchronization. Neither can you propagate information instantly. You have to at least propagate it at speed of light. That's the rate at which you can send data over the network. Okay? But it's a good definition we'll start with. Okay? And in many cases, you may say we will try to provide strict guarantees subject to clock synchronization, error tolerances, and network propagation delay. So you can't beat those 2 things. Okay? But if you can tolerate those, beyond that, you will see everything else is true. Is this clear? Okay. Yes, question. Okay, question. That's a good question. It says in CAP theorem, when you say consistency, Does it mean strict consistency or looser consistency? The strictest definition is strict consistency, but even somewhat, so there are other definitions we'll see in the next few slides that are close to strict consistency, but not as strict. Even some of those are actually hard in CAP theorem. You can't do all three in many cases. But if you go to something very weak, then it's possible. Okay, so it depends on the system how weak the consistency can be before it breaks down as per CAP theorem. But think strict consistency, if you just want to keep things simple, the C in CAP should be strict consistency. Okay. All right. Next is sequential consistency. One step weaker than strict consistency. We say strict consistency is hard. Okay, what can you do that is actually somewhat weaker than this? Okay, so here is a definition of something called sequential consistency that's a little bit weaker. Okay, so what does this say? Okay, so we will now start reasoning about reads and writes and order of reads and writes, because remember I said consistency means when the read comes in, you have to return the results of the most recent write, and we have to figure out what the most recent write is. So all of these consistency models, we'll show you examples where there are reads being made, there are writes being made, and we see for this read, what is it that you're returning from the system? Is it the most recent write? Is it an older write? And depending on what you return, you'll see that you can make things weaker. Okay, so let me define it, then I'll explain it with an example. So here we'll assume that when there are some reads and writes across processes, they'll get interleaved in some order. Okay, any valid interleaving is going to be allowed. Okay, so long as all processes agree on that interleave. So all processes say this is the order in which reads and writes have occurred, and this is what has been returned for each of the reads. Okay, each process is going to preserve its program order. Okay, which means that the process is executing instructions. You can't say if instruction A has executed before B, you can't then say B has executed. Yeah, that's not allowed. A program order has to be preserved. Okay, but we won't say anything about what's the most recent write in this case, because that will bring us back to strict consistency. The best way to understand it is with this example. Okay, here is an example, and there are two cases here. Let's take case A. There are 4 processes. Okay, they are reading and writing a single data item that is shared. Only one data item that's replicated on 4 processes or 4 systems. Okay, so process P1 is going to essentially write the value A to data item X. Maybe X is a 5. So you just write A to 5. Okay, process B is going to write B to that variable or 5. Okay, and then P3 and P4 are just going to read that file twice. Okay, when P3 reads the file first time, it sees B. Okay, then it sees an A. Okay, and then when P4 sees it, it sees the B first and then A second. Okay, and the x-axis here is time. Okay, so first thing you should realize is this can't possibly be strict consistency, because the most recent write essentially wrote B to value X. Okay, and yet when you are reading X, you first read B, and then later you see A, which was an older write. Okay, you should have, if you had strict consistency, you should have only seen B and B at this point, because A has been overwritten by B. Okay, but what we are saying is it is fine from a sequential consistency standpoint to see. So these processes are seeing the second write before the first write. That's essentially what it means. Okay, so maybe this P1 is a replica that is far away. Okay, and so the other replica has already seen a write, and the P1 has not even told the other replicas that it has seen a write, even though that write is earlier. But from a sequential consistency standpoint, we are saying any interleaving is allowed. So these processes are agreeing that the second write has happened before the first write. And that's the order in which they're seeing those writes, because you see the 2 reads are showing the writes in opposite order as far as those processes are concerned. Okay? And in sequential consistency, we will allow this. In strict consistency, we will not allow this, right? Because we always have to return the results of the most recent write. The most recent write is B. So you can never see A after that, right? Because A has actually already happened before. Okay, is that clear? So this is allowed. Okay, here's another example. Okay, same example, but P1 sees B and A when it does is to read, and P4 or P3 sees BA, P4 sees AB. They're seeing the writes in 2 different orders. Okay, P3 is seeing the second write, and then it's seeing the first write. Okay, when I see second write, it means when it reads the file, it basically sees what the P2 has written, and then it reads it again, then it sees the other write. Okay? But they are seeing two different. Here, the processes do not agree on the interleaving. So this is not allowed as per sequential consistency, because we said any valid interleaving is allowed, but all processes have to agree on that interleaving. Okay? So P3 and P4 don't have agreement on which order the writes have happened. They're seeing the writes in two different orders. Okay? So that's not allowed. Sequential. So if you are saying my system is sequentially consistent, your system better not show their processes this order, because that's not allowed. But this is okay, even though this is not strict consistency. Is this clear? Any questions here? Okay. Think about it. I mean, it's not a hard concept, but you have to think a little bit to understand what exactly has happened. Okay. We basically said strict consistency says order of writes is fixed. There's a global clock. We timestamp everything. We know exactly the order in which things have happened. Everyone sees them in the same order. Always when you read, you get the most recent version. So if there's a strict consistency, P3 and P4, because the reads are actually happening after those writes, should always see B and B. Okay. The only way they can see A and B is this: the first read has to happen between those two writes. That's the only way they'll see A, B. Because the first read is after the first write, but before the second read, you'll see an A, and then you see a B. Okay. In this case, the two reads are actually happening after the two writes, first of all. Okay. So strict consistency says it has to be B, B. But in sequential consistency, we not only allow B, A, we allow that to be in that order, even though the reads are after the two writes. Okay. So that's a loser definition. It's some called sequential consistency. Okay. You'll see another one, which is called linearizability. Okay. This is actually going to sit between sequential consistency and strict consistency. Okay. It's not one step weaker than strict consistency, but it's actually stronger than sequential consistency, but yet weaker. So it's not, we're not weakened sequential consistency further, but we added one more constraint that puts in between. Okay. So linearizability says you do everything that sequential consistency does, but you also preserve timestamp order. Okay. So if there's a timestamp in that sequence, you will actually preserve the timestamp order. Okay. If specifically timestamp of X is less than timestamp of Y, you should essentially allow those reads to happen in that order. Which means, let's just say if you had logical clocks, because we don't have perfect synchronization, if you had logical clocks or vector clocks, and two writes got ordered based on logical or vector clocks, then you have to also respect that ordering. Okay, which going back here, if these two got let's say logical or vector clock values that said that this preceded this, then you should always show AB. If they're concurrent events, it doesn't matter. You can pick AB or BA, so long as you agree, it's fine. Okay, so you do everything that sequential consistency did, but you also preserve this timestamp order. Yes, question. Okay, that's a good question. Question is, how do processes agree on the order? Okay, so for that you need a consistency protocol that guarantees this property. Think of this as a definition. I didn't show how to do this, but I haven't showed how to do strict consistency. Today we are not going to talk about how to implement the definition. These are simple definitions. Okay, so this is why it's called a consistency semantics. Consistency protocol is an implementation of the definition that says, here is what I'm going to do to ensure this guarantee. And as part of that, you will have to answer that exact question. How do processes know or agree? Okay? The protocol has to decide how it's going to figure this out, how to tell all the processes. That we are not going to look at today. We'll come back to some of this and look at it, not for every protocol, but it's at least good to know the definition. Okay? Even if you don't know the details of how do you implement all of these ideas. Okay? But it's a good question. Okay? This is why you should remember, I'm not showing any implementation. I'm just defining ideas for consistency. Okay? All right. So we did linearizability. We did sequential consistency. Here's an example of linearizability where there are three processes. Okay? Three variables that they share, X, Y, and Z. Okay, so you essentially, each process is going to set one of those variables, is going to write one of those variables, and is going to print the other two variables, which means it's reading. Okay, this is the write and this is the read. Okay, so What linearizability says is essentially you can interleave these 6 statements in any order you want. All processes have to agree on that order. Okay? And then all processes also have to agree on the timestamp in which they occur. Okay? So here essentially are 6 different interleavings, and this is what you will output for each of those interleavings. So this one is going to output 0, 0, 1, 0, 1, 1. What that means is this statement is essentially going to say x is equal to 1. Y and z have not yet been set. Let's say everything starts with 0. So when you do print y and z, you will essentially print 0, 0 here. Okay? X has been set, y has been set, and then you do x, z. So x gets 1, z has not yet been set, so you see 0. And then you set z equal to 1, you print these two, you get 1, 1, and so. So if you just execute these instructions, you will see that's what you're actually going to see on the screen. If though that's the interleaving that you agree. All of those interleavings are valid as per linearizability because they actually agree on the interleaving. You are agreeing on program order. This is program order. Okay? Program order says you always do the assignment before the print. In none of these did you actually, for any of these processes, flip the assignment and the print. If you did that, you would not preserve program order. You will see that always the assignment and the print comes in that order. Okay? And so on. So we have actually, if you go and think about it, you will see that all of the conditions that I mentioned are actually true. Okay. So I'm going to show you another example which also clarifies. It's a different consistency model, but it clarifies linearizability as well. Okay. And this one is called causal consistency. And it says causally related writes must be seen by all processes in the same order. This is very similar to saying timestamp of 2 events are ordered, then you must respect that order. We are now talking about essentially writes in this case. Okay? And I'll show you an example of what causally related writes mean. It says concurrent writes may be seen by processes in different orders. So we'll come back to the same example we saw when we did sequential consistency, and we'll see what has changed here. Okay? Process P1 is still writing A to X. Process P2 is first going to read that value and it sees A, and then it writes B. Okay? And then P3 and P4 are just doing the 2 reads. So the only thing we have changed from the previous example, we inserted a read in P2. Everything else is the same. Okay? So you first write A, and P2 is going to read it. It sees whatever P1 has written, and then it essentially writes B. Okay? So in doing this, these 2 writes have now become causally related. Okay? Because A, so think about this variable as a shared buffer, which is almost like message passing. You can think of P1 wrote A to the shared buffer. P2 read that shared buffer and got A. This is almost like sending a message saying the value of X is A. Right? So now these 2 processes have essentially have an implicit message that has gone from P1 to P2, and then this write has occurred after that. So these 2 writes are now causally ordered writes. You have to respect that ordering now, which means every other process must see P1's write before it sees P2's write. That's what is required by causal consistency. Linearizability will also require similar things. Okay? So you will see P3 sees BA and P4 sees AB. Okay? This is not causally consistent for 2 reasons. First of all, they are not even agreeing on the order. Okay? Second is they are essentially not respecting AB, because they should have both seen AB for this to be causally consistent, because you said that write is causally related to this other write, and this write has happened before that other write. Because of that implicit message passing, because there was a read sitting between those 2 writes. Is this clear what I said? Yes? Okay. Now, so this is not permitted. The only way this would be permitted is P3 has to see AB and P4 also see AB. That is causally consistent. But you can't do BA and AB. Okay? But let's go back to the old example where we don't have that read at all. Okay, that was our example. That's exactly the example shown there. Okay? If you remove this read, these 2 writes are concurrent write. There's nothing, there is no message that is going between these 2 processes that you can see. There's no read that is essentially our implicit message that goes between these 2 writes. So these 2 writes are concurrent writes. Okay? And what do we say here? Concurrent writes may be seen in different order. Okay? So in this case, P3 can see BA and P4 can see AB. and that's actually allowed. Because they're concurrent writes, we don't order them. You can see them in whatever order. Yes. Can you come again? I didn't understand. If they both see AB, one sees BB and other sees AB. Yes. If you see, if P3 sees BB, that is always allowed because you are just seeing the most recent write. So that's not a problem. And P4 sees AB, that's also, that's allowed. That's not a problem. This doesn't mean this is the only way it's called. I'm just saying that if you see two different A and B, they better be A followed by B. It can't be B followed by A if these two writes are causally ordered. However, if the writes are independent, we don't actually restrict what order they are seen in. They can be seen in two different orders. This is why this is weaker than sequential consistency. Because sequential consistency is that at least pick an order and stick to it. All processes must see that order. Okay? So if you had picked BA, then everybody should see BA. If you said AB, everyone sees AB. Here we say we don't care. You don't even have to pick an order if they are in concurrent. Only if they are causally related, then you have to pick the order that is dictated by causal relationship. Okay, so much weaker than all of the three we've seen. It's weaker than strict consistency, sequential consistency, linearizability. Yes. Okay, what scenarios do sequential consistencies give you useful properties that are better than causal, right? There may be applications where you don't want problems like this, where you're seeing things in two different order and then you're processing things in different order and things of that sort. At least if you see things in the same order, okay, that might be easier to reason with for certain applications, right? So I don't know, you can think about social media posts, right? If two users are posting or commenting on something, if you see them in one order, somebody else sees them in the other order, you don't know who commented first. Okay? You might think that this is in response to the previous comment and somebody else might see some other thing. If you're sequentially consistent, you pick one order, especially when these posts are being made at the same time, they show up in the same order in everybody's feeds. That's an example of sequential consistency. Causal consistency says that unless you have seen somebody else's post before you made it, okay, only then you show them in other order. Otherwise, I can show them in different orders to different. That might cause some confusion, right? So there may be applications where it's useful. Is that clear? Okay. Any other questions here? All right. Causal consistency. Okay. There are many other models that are even weaker. Okay. I won't go into all of them. One is called FIFO consistency that says even causal is too complicated. So we'll just assume that writes from each process are ordered, but writes across processes are not ordered. If one process does two consecutive writes, we'll just ensure that everyone sees those writes in some order, but across processes, we will not try to enforce any ordering. All of this was an exercise to ensure right ordering across processes. Okay? FIFO says, let's not even bother. Let's only look at one process at a time and see that that's actually the processes are seeing messages in that order. Okay? So that's called FIFO consistency. Okay, so it's much weaker than any of the ones we looked at. And then there are other models that don't even attempt to try to order writes because even that might be too complicated. But they use this notion of a critical section to say that let's only order things at critical section boundaries. What happens inside the critical section is not as important. So this gets us to what is called weak consistency, entry and release consistency. Okay? Three things, but the idea is exactly the same. Okay? We assume that we are going to order events based on granularity of critical sections, which are much larger units than individual reads and writes. So whenever a critical section ends, you essentially make all the writes visible in some order, okay, that you pick, but you don't actually worry about what has happened during the critical section, what order of things happening. You only look at the entry. Either you say everything is consistent when you enter, that's called entry consistency, or you say everything is made consistent when you exit, that's called exit consistency, which means all the writes are propagated after the critical section has finished. Okay? This should at least ring a bell, because last time we talked about database transactions making commits. And we said when you commit, things become visible. This is very similar to that. During the transaction, we said anything can happen. You can even roll things back. Very similar. You say only at entry and exit points do I then make things consistent. Somebody had a question? All right. So many different models. Okay. Here's a summary that shows this actually the order in which you can make them weaker one after the other. So the strict consistency at the top, then we have linearizability, then we did sequential, we did causal. I briefly talked about FIFO and the others. It's not important that you know them all, okay? But at least you should know the first 2 or 3, okay? Because those you will see in many systems. Many systems do provide linearizability or sequential consistency, and some give you causal. Strict is very not used often, but some systems try to do that as well. Okay. All right. So I'll say one more thing, and we'll talk about a very loose form of consistency called eventual consistency. But let me just talk about consistency from the perspective of the client as opposed to consistency from the perspective of the system. Okay. So far, what we talked about is what should the system guarantee for the user. And say we said this is the property that the system should provide. Okay. In many cases, that's not really what is important. What is important is what is each user individually seeing, not what the system is providing to all users. What does this user see? Okay. And what does the system do so that this user sees something in a consistent fashion? Different users might see things in different order. We already saw that. Okay. So if you just order writes and reads for individual users, you have what is called client-driven consistency. It's only what a particular client sees. Okay. So here's an example. Okay. Let's say you go and update a file, and this file is stored in some cloud storage. Okay. And let's say cloud storage is replicated. So you make an update, you write to a file, and you put it, let's say, in your whatever Google Drive or something. Okay. Then you go home, and let's just say for sake of argument, your house is far from where your work was, where you did the write, and you go and you read that same file. Okay. You expect that that file should actually have whatever you wrote previously. Okay. Okay. That's your expectation as a user. Okay. Now, it may so happen that when you read the second time, it's going to another replica. Okay. Because maybe the file is replicated, and there's one replica was close to you when you did the write, another replica is far away. Now, if the second replica shows you an older version of the file, you will say that doesn't make sense. I wrote something and I saved it. I don't see those changes here. Okay. So users might themselves see things in an inconsistent fashion. Now, this is nothing to do with the system, how it has done things. It's just an individual user, and they are seeing things out of order. Okay. This will often happen. Okay. Not for the Google Drive example I gave you, but often happens in things like password database. So you will see that you can actually go change your password on one machine. Okay. And you then walk to some other machine in the system and you try to log in, and that machine still has an older version of your password. Okay. Why is this? Because the password database is replicated. They use a old, very weak form of consistency. Okay. They have not yet propagated your change to the other password database replica. So the other database still have an old password. So you have just changed your password, but other machines have not seen it because they are using a different version of the password data. Okay. So this is where a very similar example where you make an update, you go to another machine, you don't see that update. Okay. So you want to ensure that your system is actually presenting data to users in some reasonable manner. Okay. That gives us all these consistency models, and there are 4 here. Okay. Monotonic reads say that each read should monotonically give you the same or a newer data item, never an older one. Okay. So I read something, and then I read that same file at some later point in time, maybe at a different location. I should not see anything older. I should either see the same version or a newer version, but I should not regress back and get an older version. Okay. So this example I was giving you should not actually happen. Okay. Monotonic writes see that essentially write should be propagated in the same order. Okay. So essentially, it doesn't matter if an update has not reached a replica, but the ordering should be the same. Okay. my write should actually hit replicas in the same order. Now, I should not have a write here, and then 1 hour later I go write another replica, and then some other replicas see them in a different order because you're using some weak guess. That will cause. So these are saying my write should be order, my read should be order. Okay? Doesn't matter who else is doing, because I don't care how my reads are ordered with respect to somebody else's reads. Those are all the previous protocol. This is just looking at me as a user or a process. Okay? And then it says read your writes, essentially says that a read X always returns the write X by that process. This is the password example saying I should read my most recent write. If I updated my password, I go to another machine, I try to log in, that machine should read my most recent password. It should not read an older password. That says read my writes. I should be able to read my most recent update. I should not see an older update. Okay? And then write follow reads essentially is very similar. It says a write followed by a read should essentially take place in on the more same or more recent version. Okay? So very similar ideas, but this is saying let's try to think about consistency for each individual users. Let's not try to take the multiple users and try to come up with some interleavings and say what should a third user see about those two users. That's too complicated. Let's just try to show each user a consistent view of the system. That's what this is. So it's all of these are much weaker than anything else we studied, because they're only thinking of one user, not multiple users. Yes. What's the question again? Shouldn't the system enforce these rules? No, they don't enforce. That's the problem. Most systems will actually have very poor consistency guarantees. They will not even give you this, which seems quite reasonable, even though it's quite weak. I gave you the password example, right? It's actually, if you can try this, if you may get locked out for a bit on the lab. You go to the lab, you go to one machine, you change the password, you log in on another machine. Sometimes it will not see the password. You will see your old password. So you will not be able to log in with your newest password. You might have to enter the old password, and maybe an hour or two later, the changes will sync, then the new password will show up. Okay? And that's because systems have a very lax view of how to keep consistency guarantee. Because it is so expensive, right? They will say, let's just do something that is weak. And I'll talk about one that's called eventual consistency. You will see that that's so weak that all of these problems can actually occur in those systems. Okay, all right. So let's get to eventual consistency, which is essentially the weakest possible model you can think of. Okay? But this one says no guarantees. Okay? Eventually, my change will propagate. I will not guarantee anything on whether it will propagate, how long it will take to propagate, but eventually it will do after maybe long periods of time. Okay? So this is actually surprisingly weak and often used in many systems. Okay? Domain name system uses this. So if you actually go and update the IP address, let's say you have a URL, www.umass.edu, you want it to point to another IP address, you make that change. It may take 24 hours for the rest of the world to see it. Okay? Until then, some will see the old version of the IP address, some will see the new version. Things will stay inconsistent for some period of time, okay? As much as 24 hours. Okay? That's what this is a very weak form. Okay? Same thing about the database. Okay? So I mentioned the password example. Okay? Password example, same thing. So the way they set this up is these databases will synchronize with one another once an hour, after some amount of time, periodically. Okay? So until then, they will be out of sync. Okay? But every hour, they'll say, okay, let's propagate all the updates, and then they'll synchronize. Okay? So a lot of these systems use these type of techniques, which is why you have this. And as it turns out, all your cloud storage, Dropbox, OneDrive, iCloud, all use eventual consistency. There's no guarantee. Okay? You actually have two machines. You go and you put a file on one machine and you update OneDrive, Dropbox, any cloud database. You go and see on another machine. It may not have shown up. It takes some time. Where the cloud storage is giving you no guarantees of how long it will take for your write or changes to propagate. Okay? It will show up, and typically good ones might propagate them in seconds. Okay? Some might take minutes, but it will take some time. Okay? The system says no guarantees. It will happen eventually. Just be patient and wait. Okay? So this is the model that most large systems actually use. And so it's good to understand what this means and how it is actually done. So essentially, there is a very weak guarantee. All changes are eventually sent to other copies or other replicas. Okay. So how does this actually work? Okay. So essentially, what the formal definition of eventual consistency is, in the absence of any more updates, all replicas will eventually converge towards identical copy. So say that you stop making updates, and then after a while, all the replicas will converge to one version where everyone has seen whatever changes have been made. Okay. But while changes are being made, the replicas may be in different states, that some replica have some data, others have some other data, but they are not all seeing all the data all the time. Okay. So it's very cheap to implement. Okay. This can often cause write-write conflicts, okay, because you're not ordering writes and so on. And you will see this also if you use Dropbox and these other systems frequently. If you have multiple machines, you go and make changes to the same file on two different machines close to one another. The system will not know which is the most recent version. It will say, I have two copies that were changed more or less at the same time. That's a write-write conflict. And it will say, here are two copies of the file. You go figure it out, and you say which one is newer, or you merge it or something like that. Okay? So this will also, you will see every cloud storage system will actually flag this when you do these types of. Okay? If you had some strict guarantees on consistency, you would not have that problem. Okay? You would have actually known which one happened before which one, or something like that. Okay? So very cheap to implement, but still gives you some write-write conflict, and things are fine so long as user accesses the same replica, you go access some other replica, you may get older data. Okay? But let's now see techniques to implement. This is the first time we are actually now going to turn our definition into an actual implementation. Everything I talked about so far was just definition. Okay? Strict consistency, linear. I did not say how to implement any of this. This is weak enough that we can actually talk about implementation. Okay? We'll talk about two techniques. Okay? Their first one is called epidemic protocols. Okay? This was a technique that was designed, I think, almost 40 years ago now, okay, in a system called Bio. Okay? And the main new idea in Bio was, it assumed that the replicas had what was called weak connectivity, which means replicas often got disconnected from the network. Okay? So there was no way of implementing anything strict, because if the replica is just disconnected from the network, there's no way you can tell the replica something has changed. Right? It was not even there to that you cannot communicate with it. So they said we have to do something weaker. And the reason this was true, by the way, is these were the old days where mobile computing was just becoming sort of something that researchers were studying. And mobile devices are not always stay connected. Even today, your laptop, if you close the lid and go somewhere, disconnected from the net. So you have all kinds of mobile devices that are fundamentally not always connected to the network. So how do you ensure consistency in that scenario is what they are looking at. And then they said, let's come up with this notion of weak consistency, or eventual consistency rather. And how are we going to do this? They came up with this idea saying, let's use this notion of the epidemic protocol was essentially developed based on theory of how diseases spread. Okay? How do diseases spread? Right? So it comes from pairwise physical close proximity or contact. Right? So this is how cold is going to spread, or this is how COVID spread. You are sick, you go near somebody, inadvertently you pass on your germs, and the other person becomes sick, and then they do the same thing, and it's essentially going to pass your germs to somebody else. Okay? So if you look at that concept, you can say this is how I am going to, as in the system, spread updates. Okay? When a change is made to a replica, okay, we are going to essentially call it an infected replica, because it has a change it wants to spread. Okay? How is it going to spread that change? It will talk to some other machine at random, okay, and then essentially try to spread the change by saying, here's some change I received, now go spread it yourself. Okay? Exactly how diseases are going to spread. So it's the key thing here is pairwise exchange of updates, where two replicas connect. Okay? You basically say replica I connects randomly to replica B and say, here are some changes I have, maybe that one also sends you changes, and then you exchange some of them. And then you do repeat this randomly over time, all the changes are going to spread to the system. Okay? So Essentially, it's pairwise spreading of diseases. So the terminology here is as an infective store. This is a store or a database or a system that has some changes it wants to send to someone. Okay? Susceptible store is the one that is yet to see that change. Okay? And the goal of an infected store is to make all the susceptible store infected. So if everyone is infected, okay, all of them have seen the change. Okay? That's the basic idea. Is this clear what I'm saying? Okay? So this is essentially a randomized algorithm. Okay? So it's called anti-entropy. It's completely randomized. So you have n replicas. Server P going to pick a replica server Q at random. Okay? And they exchange some updates saying, do you have any changes I have not seen? I saw, and you basically look at what data you have. The other one is what data they have. You look at the difference and you just exchange all the differences. Right? So this is exactly how Dropbox will synchronize your laptop with the cloud server or any of your storage services. Okay? They will essentially, your laptop will periodically connect to the server and say, I have these new files, here they are. And you'll say, server, ask the server, do you have any new files I have not seen? And it will pull those. Okay? So this is pairwise exchange of information. Okay? In this case, there is you can contact any replica. You don't have, in the cloud storage, there's a distinguished replica, which is the server. All the replicas contact the server. Okay? But you don't need to do that. You can do peer-to-peer exchange where any replica contacts any other replica and say, okay, I can either push changes, okay, I can pull changes, or I can do both push and pull. Okay? So completely randomized technique. Okay? P picks a server Q at random. Okay? Every so often you just say time to pick a server, you connect to the server, you push, pull, or both, and then you go or do something after a while, you repeat and so on. Is this clear? Okay. So as simple as it gets. Okay, that's called anti-entropy. Okay. There's another one called rumor mongering or gossip protocols. Okay. This is exactly how a rumor is going to spread. How do you spread a rumor? Say you have some interesting information, you want to essentially tell your friends, you will call your friend at random and say, okay, I heard this interesting rumor, and then you spread. And then your friend might repeat that and so on. Okay. Now, just as rumors will stop spreading after a while, because if it's stale information, you say, I'm not going to call 5 more people. Everybody seems to know this news already. Okay. So essentially, there's a back off in rumor mongering. There's the same thing here. Okay. After you spread the rumor a few times, you'll start tossing a coin. Should I continue to spread a rumor or not? So if the coin says, let's say heads, you'll say, I will call some more people. If it says tails, you say, I'm done. I'm not going to tell anyone because everyone seems to know it. Okay? So there's a probability by that you have a coin toss that tells you when you as a user, or in this case a system, will stop spreading that update to someone else. Okay? So hot gossip items will start spreading quickly, and after a whole bunch of systems have seen it, maybe there are only a few systems will continue to spread it, and others have stopped spreading it. Okay? Now, in this technique, in rumor mongering, there is going to be a small probability that there will be some store that will never see a change, because everyone has just said, I stopped spreading the rumor, and nobody contacted that store. Maybe it's not the person, not a good friend of anyone. Nobody actually called them to say, here's this piece of rumor that I want to tell you, something like that. Okay? So there is always a chance that some replica will always say out of sync, never got that update. Okay? In this other case, anti-entropy, that's not going to be the case, because any system can pick any other system at random and ask for updates. Okay? So eventually, the update will spread. It may take a long time, but it will spread. Okay? In this case, you have actually a mechanism to stop spreading updates, just the same way rumors, you may just not call any more of your friends to tell them about this news or something like that. Okay? So this class of protocol is called gossip protocol. So both are randomized, okay? But in this case, it's randomized with some stopping. In the other case, there is no such thing as stopping. Basically, you keep going until everybody's seen it. Okay? Okay. Question is, what is K? Is it the number of nodes? So in this case, K is the probability, 1 over K is the probability of stopping. Okay? So if K is set to 2, you toss a coin, probability half, you will basically say, I'm not going to spread it anymore. Okay? So you want to keep the value of K high, so that the probability of continuing is high for a while. Okay? If you set it to be small, then you might stop quickly and the rumor doesn't spread much at all. Okay? If you keep it the other way around, you will keep contacting friends. They say, I already heard this 1 hour ago. You're just telling me something I already know. So you are essentially doing extra work trying to spread a rumor when the update is already. So that's a tunable parameter that tells you how many nodes you will contact before you stop. Okay. Yes. Okay, good question. How does rumor mongering or gossiping guarantee eventual consistency if nodes are going to stop? So you'll see that it does not guarantee all replicas will receive the update. So it's not going to give you eventual consistency in that fashion. But if you think about it, even anti-entropy might take infinite time to spread the update. So it's not like eventual could be so long that it does matter. It's no better than not receiving it at all. Because there's no guarantee the update will spread anytime. So it may take 10 years, right? Because you might have a technique that randomly picks some nodes but not other nodes. Because it doesn't say how to pick a node or anything like that. So some nodes may take a very long time to receive the update, which is no better than not receiving it at all, because for all practical purpose, those nodes are not seeing it. Okay? So eventual consistency is so loose, there's really no guarantee. So there is no such thing as guaranteeing eventual consistency, because it's like it can take an unbounded amount of time to get all the updates. In this case, that unbounded amount of time is infinite. That is the same as saying you don't get it at all. Okay. Any other questions here? Okay. So I want to say one more thing, and then we will end, which is when you have epidemic protocols, spreading new changes, new files, updates to files is the technique I talked about previously. Okay? But there's an interesting point of if you actually delete information, how does that change? That's also a change. Okay? You deleted something. How does that spread? So let's take the Dropbox or OneDrive or whatever iCloud example. Let's say you have a shared cloud storage and you delete a file. Okay? So if your machine then goes and contacts the cloud storage and say, I have 3 files. How many files do you have? It'll say, I have 4 files. Okay? And the file that you deleted is still on the cloud storage. And you might think that that's a file you don't have because it's not in your directory, and you'll download it. And the file you deleted has just reappeared. Right? So this all, if you base, so essentially removing data, if you don't do it well, will just not actually work well, because you'll recreate deleted data and the file will just show up again as if it has never been deleted. So you can't simply just look at file directory contents and say, which file do I have, which file do you have? Let's just transfer information. If I don't have a file, you send it to me. That doesn't quite work when deletions are actually also part of the story. If you are just creating files, it works fine. Okay? So what will you do? Okay? Essentially, you have to actually keep track of deleted files by creating what's called a death certificate. Okay? So you delete the file, but then you create a special file saying this file was deleted. Okay? So you then, when you compare two directories or content, you say, is this file actually not something I never had, or was this a file I deleted because I have a death certificate that I kept saying the user actually deleted the file? So I'm not going to recreate it by downloading. Instead, I will actually spread the death certificate to other nodes and say delete the file. So that certificate spreads, and then you start deleting the file. Okay? So that certificate is an update saying the file is deleted. That's the last update you make to a file before it disappears. But if you don't keep any record that the file has disappeared, your file will magically reappear after. Then all the system you built will not really work as intended. Okay? So you have to essentially track deleted data by creating extra information, which we just call death certificate, spread that and cause the file to get deleted. And of course, eventually you want to clean up your death certificate. Otherwise, your directory will be filled with death certificates from files you deleted 10 years ago. They'll still be sitting there. Okay? Because there may be some node that hasn't seen your death certificate, may still store an old copy of the file. So you have to wait a while before you do it, but eventually you want to start cleaning them up as well. Okay? So that's basically it for today. So we went through an entire chapter of the book. So that was quite a bit of material we covered in one lecture. I will put that link to that chapter from the book. Go and read it. Some of the concepts, as you will see, are definitions. You have to understand them a little bit Once you get the hang of what it means, it's not very hard to understand. Things like eventual consistency are much easier to understand because they are all using simple randomized technique. There's a way to understand them much better. And these are the techniques that are actually used, okay, in many systems, not any of the ones we started with, like strict or sequential linearizability. In the database world, you do have some of these techniques like linearizability being used, but most of these other systems simply use eventual consistency. Okay, so we'll stop here. Yes, so final question is.
So is it just 100% of this because we start with a straight line and we go down lower something from this line?
Yes, so I think if you relax the consistency in CAP theorem, so question is, what happens if you relax the consistency in the CAP theorem? What do you gain? That's your question, right? So if you relax the consistency, if you say consistency is eventual consistency, that means you gave up C. Okay? You weakened it to eventual consistency. Now you have availability and partition tolerance, which means that even if the network is cut into two, some replicas are on the left half, some replicas are on the right half. Okay? You can continue to access them. Okay? They will not be consistent because you will modify them. They can't talk to one another. They will start diverging. You can continue to access them. So they are available to you. And you go in partition tolerance, which means network is down, you still have the system up and running. Okay? So this will often happen where there are network outages and so on. Okay? If you want to keep consistent, all the replicas will block, and we can't take any changes because we can't propagate the changes. So we don't know what state other replicas are in. So I have to fundamentally not process any more requests. Right? So if you have databases that actually give you ACID properties and you keep two databases on two locations, okay, and the network dies, the database can't process queries. So your bank transaction will start failing. But one database is now disconnected, so you can't propagate changes. Right? So it can actually cause problems if you want to ensure strict consistency, because you will have to give up. I cannot tolerate network outage. There's a network outage, system goes down. Right? On the other hand, if you say I give up consistency, all kinds of failures I can tolerate, but because replicas will go out, be inconsistent. And if I'm willing to tolerate that, and then later on I synchronize, that's fine. It's all a trade-off. There's no right answer as to which property to give up. Depends on the application. Okay, all right. So I'll end here, but I did want to make one announcement. So Monday, I'm going to cancel the lecture. Okay, so there's eclipse. So it's actually during the lecture time. Several students wanted to see if they could skip class. So I'm just going to not have the lecture on Monday. We'll have a makeup class maybe in a week or two once I have figured out what time to hold it up. Okay, so next week, only one class on Wednesday, no class on Monday. Okay, you go see the eclipse. Even here is 90% eclipse, but use glasses. Don't go see it without proper eyewear. Right? Okay, so let's drop.